Okay. Good afternoon, ladies and gentlemen. My name is Rackl. I work at the Technische University of Munich. However, the work I'm going to show today is something I did during my master's thesis at the University of Applied Sciences in Regensburg. And it is about material testing and hyperelastic material model curve fitting for Ogden, Polynomial and Yeoh models. Now, first of all, I would like to give you some background information about why did I do that, why did I concern myself with hyperelastic material model fitting. Then, how does the whole process work, because I believe a lot of people here don't have the necessary background to know what it's all about. Of course, state my problem, then show you the materials and models, so how did I solve the problem, and of course in the end show you the results and do a little conclusion on, well, one of the special points we discovered during the work. So, on the background information, why did I do that? Well, the reason I did it is because I had to do a static structural investigation on a new medical device which uses silicone as a sort of suspension material, and the silicone we used was sort of rubber-like. So if you consider rubber, which has a really elastic behavior and can be deformed very largely. The method we used to do the computation was the finite element method, which is really common in mechanical engineering. So the first question I asked myself was, well, how do I model silicone using finite element method? The answer from literature, well, use hyperelastic material models. Well, next question, what are hyperelastic material models? There are two types. There is a micromechanical type, where the material constants are derived from actual material tests. So there are special tests where you can get the material constants from. However, there are studies which suggest the use of the ones which are shown on the left here, the phenomenological models, which are based on regression analysis. So there is no really physical relevance to any of the material constants. It's more about just making sure that the outcome is correct, but nobody really cares about what the material constants are like. Now, the way it usually works is, first of all, one has to carry out material tests still, because we're still modeling reality. Then, second part is curve fitting, so basically adapting the material constants of the models in such a way that they closely match the measured stretch strain curves in this case. And for the last part, do the validation, of course. Model the experiment using FEA and make sure that the measured response is the same as with the simulated response. Now, the three models we selected were the Ogden model, the polynomial model. I guess some people are familiar with the Mooney-Ripley model. It is a special case of the polynomial model. And the Yeoh model, which is not exactly new, but I think it was developed around 1993, so it's not as old as the upper two. Okay, but what was the actual problem? The actual problem was that we were using a commercial software which offers curve fitting for hyperelastic models. However, the order to which these models could be fitted were restricted. So what I have to say, that each of the models I just showed, so each of these models can have different orders. So there is a first order Ogden model, there is a second order Ogden model, there is a third order, and so on. And the software used, ANSYS, which is a very widespread software. It is a really good software for finite element analysis, and the user can input any order material constants for any of the models. However, the fitting algorithms within the software only allow for the fitting to a certain degree. So, for example, I might just be able to fit up to a second order Yeoh model, and then it just stops, even though I could input higher order material constants. I don't really understand why someone would implement it this way, but it's how they implemented it. Now, how we went about solving it is creating a Scilab script which gets us rid of these restrictions. Well, but before we began, we had to carry out material tests. In this case, we carried out two really simple material tests. The first one is the so-called bonded compression and tension test, and the second one is a simple shear test. Now, the simple shear test, I don't really want to talk too much about it. It's a really simple test. We had a really thin layer of silicone between two steel strips, and we selected such a thin layer because our application did also use such a small layer. For the compression and tension test on the left-hand side, it was a little different because if you imagine that this rod and this rod are being stretched or being compressed together, the silicone, which is bonded right here and right there, it can't really expand. So the final shape is going to look something like this. This, like this. And this special condition makes it necessary to correct the measuring results by a certain factor. And there have been quite a lot of studies on what this factor should look like and how to compute it. We used the one as stated in my source number 8. It's a paper by Horton et al. So after doing all this, we finally got to our stretch and stress curves, which we could then use to fit our material constants to. However, before we can fit our material constants, we need to derive the functions and implement them in Scilab. I'll just show you the process using the Yeoh model in tension and compression. It's pretty much the same for all the other models. So what we had to do is derive one equation for compression and tension and the second equation for the simple shear test. And doing this for all the three models leads to a total of 6 equations we had to derive. The whole way how it's done is basically given in literature. So this is the Yeoh model as stated in literature. The strain energy basically connects to the elastic energy stored within the material. So if you deform a rubber, it will go back into its initial shape, and the energy stored is basically shown by the W right here. The CIs, which are here, these are the material constants we are looking for, but in order to get there, we first have to see what the strain invariants are, which is the I1 in this case. Sorry. Okay, looks like I'm missing a slide. Anyway, of course, there's a formulation for the strain invariants in literature. So all we had to do is look them up and basically copy and paste them for the correct loading case. Then, well, we talked a lot about the stretch stress, but it didn't really show up so far within the equations because this doesn't really have any engineering stress on it. It doesn't even have any stretch in it. Now the stretch equations should actually be down here, but you can find them in the literature. More important, the equation shown in point number 3 shows the relation between the engineering stress and the stretch, which is basically the lambda in here. Next step is take all the equations as shown, combine them, and get the equation for tension and compression of an nth order Yeoh model. This is just applying basic maths, looking up literature, and well, combining it all together. But just to let you know, this is kind of how the equations look like, which we implemented in Scilab. Now, what does the optimization problem look like? Well, the optimization problem looks something like this, and this is also the workflow we implemented in the Scilab code. We start with the material model functions. In this case, for a Yeoh model, there are 2 of them. compression tension and simple shear. Plus, what we also have is measurement data. So this is given, this is being derived from knowledge from literature. And in the end, what we would like to get is a vector with all the material constants, which is down here. Now, how do we do that? Basically, it is a simple optimization problem. It is a regression analysis. So what we did was just specify a starting vector for the material constants, which was sort of arbitrary. Do a computation using the stretch data for measurements, so here and there. Compute the engineering stress in tension and compression, as well as for simple shear, and compare it to the data for measurement using two area criteria. I will talk about the area criteria on the next slide, because for any optimization it is important to know what the quality function looks like, and in this case the quality function was just adding up these two errors. Then, last step, put the error into the fmin search function, tell it to minimize the error using the material constants vector, which is fairly easy. Now, I said that the quality function is important, so in this case we use two different quality functions, which connects to how the functionality is implemented in ANSYS. Because we were creating a Scilab script from scratch, we had to compare them to something from which we know it is correct. So we used ANSYS. So at least we can compare the lower order models we fitted to the ones we got from ANSYS. Now, just quickly saying, there is a normalized error and there is an absolute error. Of course, the normalized error gives you a better curve fitting, as I would say, in most cases. But just to let you know, because it's going to say normalized and absolute on some of the later slides, that we use two different criteria. Of course, since we were doing regression analysis, we also have to check whether whatever we got as a result is close to what we're looking for, and just to get a number to compare our results, we use the adjusted coefficient of determination, which is a little different from the normal coefficient of determination in terms of adding, basically adding a negative aspect if you use more constants. So if I was fitting a model using 20 constants, it would tell me, well, you have got a nice fit there, but you use 20 constants. Maybe you should reduce your constants, because you can fit almost anything using a dozen of material constants. And like I said before, we also compared the results, at least for the lower order material models, to those from ANSYS, so we could validate our code and verify our code to see whether we implemented everything correctly. So as for the results, I will start with the Ogden model. Well, these are what you can see here. Basically, on the left column is the respective order of the model, which error criterion we used, the number of parameters which is connected to the order, then the results from ANSYS, which stop here because it's just not possible to fit a higher order model in ANSYS, and the results from our Scilab script. Now, I guess everybody's able to see that those are not the same, and I will come back to that on a later slide. Just for now, have a look at this model right here, and the results shown from the comparison shown between the measurement in blue and the result from our model. The connection is really, really close. I mean, you can see it's 0.998. It's 0.9. Actually, it's 0.90. So it's really close. So of course we ask ourselves, well, that's different, but we still get a good fit. So what's going on? But I will come back to that later. Let's first have a look at the polynomial model. And this time, for the polynomial model, we got a perfect fit. In this case, for 3 different models, and as you can see, it's basically exactly the same between ANSYS and Scilab, so we know that whatever we did in Scilab is correctly implemented. Just to let you know, this is basically what is shown here. Also, there's a good, the models correspond really well. Just to see that this is actually what the stress-strain curves look like. Oops. This is what the stretch curves look like, and yeah, it's really close. So I don't think there's too much to say about this. Third case, which was the Yeoh model. Well, the Yeoh model, as shown here, as you can see, it stops for ANSYS. It stops here. So all you can fit in ANSYS is a 3rd order Yeoh model, whereas in Scilab we can go up to whichever level. There is no restriction for the script we wrote. And looking at the first model, which is the one we could compare, it also yields exactly the same results. Again, this is what the fit looks like. However, the Yeoh model tended to show results, as you can see here. I guess this is somewhat okay, even though it's not perfect, but the course of the curve here, going like this, is not exactly what someone wants to see, because it might be really close to the measurement data, but the course is not really predictable because it changes direction a couple of times. So it's not really the model we preferred. So in the end, we ended up choosing this model, which is a simple 2-parameter München model. There is another reason why we chose a 2-parameter model, which I will talk about in a second. So, for the conclusion, well, the curve fitting script we wrote, it can fit any other Ogden model, it can fit any other Yeoh model, which is a huge advantage as compared to ANSYS. And we implemented a 1st and 2nd order polynomial model, as well as the München model as one special case, just because it is really widespread in hyperelastic material modeling. We also validated the lower order results against ANSYS, which worked well for the Yeoh model as well as for the polynomial model. But one of the problems we had was that especially the higher order models tend to instabilities. And those instabilities can crash your finite element analysis computation. So even though we were able to fit these higher order models, we could not really use them because our finite element computations kept crashing. And afterwards, we kind of got an idea why ANSYS just implemented a lower order fitting, because it appears like most higher order models are really unstable and just there is no use for them, because it looks nice, you get a great fit, but your computation keeps on crashing all the time. So from a mathematical perspective, it's good, but from the practical perspective, they're more or less useless. Well, but what happened to the Ogden model? You saw that the parameters didn't really fit. So, of course, we had a closer look on what's going on. Now, we saw the differences. And what I didn't show you were results for lower order Ogden models. Now, here is one result. So, what do you see? Well, you can see that we compared a simple 1st order model, which consists of 2 parameters, and they're close. So, to be honest, we couldn't really figure out what's going on, but the lower order models were all really close to the answers. Now, of course, we had a look in literature to sort of see what's going on and maybe find out what's going on. We also checked the validation results. The results you can see here are the actual measurement results as measured in the material test. So you're not looking at stretch and stress curves, you're looking at force displacement curves. So this is really what our testing personnel measured on the physical material specimen. And using the Ogden model I just showed you, not the one with the 2 parameter, but the one with the 8 parameter from the first validation slide, it gets close. So it's not, there's no way that, which I would agree on, that it's not correctly implemented. Now, to be honest, we still don't know what's going on. But from what we see here, well, this is good. This is good. Well, this is not perfect. It's without a standard deviation, but I wouldn't say it's completely off. You can see the difference right there. This one stays sort of between 10%. This one also stays within 10%. This one, well, it goes up to 20, becomes worse in the end, but basically it's not bad. The beginnings right here, right there, and these are just numerical effects. Because if you're around 0, small deviations will give you a huge difference in percentage. Now, well, so the Ogden model appears to be correctly implemented. And the differences we saw, the differences in the material constants between the ANSYS and our Scilab script, we believe they are just a result of the nonlinear nature of the problem. So the polynomial model as well as the Yeoh model, it's just a linear optimization. So you have to end up with the exact same result. The Ogden model is a nonlinear optimization problem. So you could run into a lot of different problems. Except from that, there is more than one minimum. Depending on your starting values, you may end up in different local minima. And even if you use the same starting values, you might end up with different material parameter sets. So these are the only differences we could identify, or these are the reasons we could identify. And as for the last point, the optimization algorithm we used was the fmin search, which uses an Eldamite optimization and is implemented in Scilab. But the ANSYS manual does not tell which optimization they are using. So there is a good chance that the optimization is different between a Scilab script we wrote and ANSYS finite element software. So unfortunately, since we do not have the ability to look into the ANSYS source code, we couldn't really figure out if this is the problem, or well, not the problem, but the reason for the differences. So generally, it was really important for us to have the script. But summing it up, if you ever have to fit hyperelastic materials, I strongly suggest you to try out lower order models first, because even if you might have a really nice fit in a stretch and stress curve, it might end up crashing your simulation over and over again, because higher order models just tend to be unstable, and there might not be the need to do higher order model fitting. Now, from my side, this was my presentation, and thank you for your attention.